So rotational inertia is the version of mass that we use in rotational motion, which leads us very quickly to the equation that we'll use for torque, the relationship between torque, acceleration, and rotational inertia. So Newton's third law, I guess I should write this in Newtonian terms or in linear terms first. In linear terms, it was the sum of the forces over the mass equals the acceleration. So the rotational version of that, we're just going to replace that with all of the rotational analogs. Instead of acceleration, we'll have angular acceleration or fish acceleration. And then we'll have the sum of the torques acting on the object all over the rotational inertia. So this equation here relates all of those different values. But something important to realize and to connect here is that we have some other equations that describe rotational motion and torques as well. So we know that torque can also be written as R times F. So if we look at this system right here that I've drawn over here, where we have like some kind of a disk and a force is being applied to cause an angular acceleration, I could solve for the angular acceleration by combining together these two equations. And I could say that the angular acceleration is going to be equal to R times F all over the rotational inertia. That can also get a little bit more complicated if we realize that this is a disk, and therefore the rotational inertia of a disk is 1/2 mr squared. So I can now put that in there, and we'll get something that looks like the angular acceleration is equal to, from the torque equation, R times F, divided by, from the rotational inertia equation for a disk, 1/2 mr squared. And this actually would end up simplifying because we have an R on the top and two R's in the bottom. So I can simplify it to something like 2F over mr equals the angular acceleration. We could even go a little bit further than that if we wanted to figure out the linear acceleration of a particular point, because we know that linear acceleration, alpha times r, is equal to acceleration. So acceleration over r is equal to alpha. So then I could plug that into this equation. Oops, I made a mistake earlier. This should be an r right here, not an f. Do r. So I could plug that into this next equation, and I could say a over r. Oops, I should do that red. A over r is equal to all this green stuff, 2f over mr. And in this case, we find out that the acceleration, the linear acceleration of this object, would be 2f over m. Notice, of course, that we have something that looks pretty familiar for the acceleration of an object, the f over m, and that 2 is left over from the rotational inertia. We picked it up way back here. So rotational inertia problems and torque problems have a tendency to kind of pull equations from a lot of different places, but it's always the same equations. The big ones that you guys want to focus on is make sure that you realize really often that you can combine these two equations into this second equation there. Only other thing that I want to say on rotational inertia and torque is if graphs start showing up, since the relationship between angular inertia or angular acceleration and torque looks like this, if acceleration is a y-axis for our graph and torque is the x-axis on our graph, then the slope of that line would be 1 over I, because that's the stuff that's left over in my equation. The same thing holds true if I was to graph the angular acceleration versus 1 over I. There's also a torque in there in the equation because it's torque over I. And so we could find out that the slope of this graph would be torque. And if we were given something like the radius, we could take the slope divided by the radius to figure out what the force applied is. But notice that if we are graphing this, we have to graph it versus the inverse of the rotational inertia, not the rotational inertia. If you graph it with the rotational inertia, you'll instead get, if you're graphing it like that, you would instead get an inverse graph, which is not linear, and we can't use anything to figure out the torque there as easily. So there's some of the rotational inertia and torque interactions that you guys will need to know for class and for the AP exam. Thanks for watching.